Hey there, everybody. Welcome back. This is chapter 13 in Calculus 3. This is the fall 2022 semester at College of the Sequoias, and this entire chapter is on multivariable functions and partial derivatives. Let's just get right into it. So multivariable function, what is it? It's a function of more than one variable. And you've seen them all before, or not all, but you've seen them before. Like area of a triangle, 1/2 base times height. It's a function of both base and height. If we look at the volume, volume is a function of length, width, and height of a cube or a rectangle. So you're familiar with them, and we're just going to start working with them. So the domain of a multivariable function is all values that produce real numbers when you plug them in, unless other restrictions apply, and we call the other restrictions constraints. So a function of n variables would have x1, x2, up to xn, is a rule that assigns a unique real number to each point in the function. In some set D, D is the domain in the n-dimensional space. So let's just take a look at an example here. If we say f of xy is the square root of 2x plus y plus 2 all over x minus 3, we could ask, well, first off, what's the domain? The constraints here we have is the denominator can't equal 0. So we have x minus 3 cannot equal 0. And for us to produce real numbers, we need the value in the radical to be non-negative, so greater than or equal to 0. So those are the two constraints we have. And so, well, how do we graph this kind of thing? I showed the constraints here. You can see the line. This is just not, this isn't the graph in general. But this is, we have the blue line right here is the y is greater than or equal to 2x minus 2. The dashed line says it does not include x equals 3. And the way you can find out which side to use, you could plug in a value, plug in like 0, 0 into this, the top constraint 2x plus y plus 2 greater than 0. And you'll find that 0, 0 makes that sentence true. So it's everything above the blue line, except for the red constraint. And you'll notice when we plug in different values like 1, 0 or 12, -1, we get different values for the function. And not, this seems like a weird way to show it. I'll show you on other graphs in the future coming up. Like normally when we do y equals f of x, what the f of x equals is on the graph. Well, where's my function here is f of xy. We should have something else that shows this. And we'll see that on the next problem. I didn't want to graph this one in 3D. When we write the domain, this is how we write it. We say that x and y are the variables, put a vertical line, and then we list the constraints. They show what the requirements are for it. Let's take a look at another problem here. We have f of xy equals square root of 4x squared plus 9y squared minus 36. Again, we can look at the domain by seeing where the value inside the radical is greater than or equal to 0. And we'll see we get an ellipse. X squared over 9 plus y squared over 4 is greater than or equal to 1. And the way I did it is I did a test point. And 0, 0 was often the best test point because plugging in zeros are really easy. I don't need a calculator to figure out 0 plus 0 is greater than or equal to 1. That's false. So 0, 0 doesn't work. And so it can't be inside the ellipse. So I shade outward. Do note that if it had been the other way, where it was 36 minus the 4x squared and minus the 9y squared, like everything was the opposite sign, the fill would have been on the inside. Okay. Let's take a look at another one. F of xy equals 4 minus 2x minus y. Here I'm going to do this one in 3D because, well, I want f of xy to the function to show up, the value of it to show up on the graph. So I'm going to set that equal to z, which is a common strategy, give it a third dimension like this. And if we do that, we can see that we get 2x plus y plus z equals 4. And so that's just a plane with a normal of 2, 1, 1. And I just plotted 3 points that are on the graph and drew the triangle, and you can see it going onward. Well, what happens if I do that up here? Let's try to do this one in 3D. So I set z equal to it. And so I can square it. Z squared equals that. I get everything on the same side. And I got x squared over 9 plus y squared over 4 minus z squared over 36 is 1 equals 1. This is a hyperboloid in one sheet. And notice my graph looks terrible. I plotted the ellipse in 3D just fine. But then when I tried to show what looks like a nuclear reactor like structure, my three-dimensional figure just doesn't deliver. And that's it for this section. We got a couple more parts in 13.1, but peace.